Now it's working. Fantastic. Okay. Are we hanging in there? We ready to go? It's been a long week, right? Yeah. Well, it doesn't get any easier. You get into this space, it doesn't get any easier. If only it did, right? Okay, so today we're going to continue along the theme of dealing with signal-to-noise ratio. So for those of you who have taken statistics, it's all about signal-to-noise ratio, isn't it? So before I get started, because it's a bit dense, what I'm going to talk about is a little dense, I'll try and make it as easy as possible. And it's not, when I say, or when anybody says, they'll try and make it as easy as possible, it's not patronizing, right? You have to realize that. It's just because you don't know it. So for anyone who doesn't know the material, it's difficult. So by making it easier, it's just an introduction, a way of getting you into the material, right? So never be offended as a student or as a faculty if someone is making something easier for you. It's nothing personal. So this is work that my PhD student is doing. So she's in the Department of Statistical Sciences, okay? So she is not a machine learner. She's not a medical scientist. She's a statistician. And she's doing her PhD in statistics, but inevitably, because she's doing it with me, it crosses over into the world of medical imaging, okay? But before I get started, let's talk a little bit about statistics. So what is the purpose of statistics? Why do we need statistics? We kind of touched on it earlier on in the week. So why do we need statistics? I know you guys are all looking down. This is exactly like when I teach statistics. Nobody wants to answer. But why do we need it? Who here has done statistics for their degree, or for their work, or for anything? Okay, wow, I'm going to say many of you, most of you have probably done it, but you just didn't know. Okay? So for those of you that said they did statistics, I believe you. I'm sure you did statistics because you're aware that you had to do them for your project, right? But for the rest of you, do any of you deal with data? Measures. Does any of your work deal with measures? Something you measure, a numeric measure, a proportion. Any of your work? So now put up your hand if any time in your life you've had to deal with numeric data, with data. So you know the difference between a data and a single measurement, right? So meaning you have multiple measures, you have a whole pool of data. Now put your hand up if you've had to deal with that kind of data. Okay, so if you're not putting your hand up, it's because you're asleep, or you still don't understand what I'm trying to say about data. So in your daily lives, you deal with statistics, you just don't know it. Okay? So every time you talk about you wouldn't even say, let's say we don't even say a mean, let's say an average. An average is statistics. If you ask somebody, what's the biggest in that? Is that statistics? It is. Because what is meant by the biggest? What does that imply? The biggest. What do you need to know in order to give me that answer? Yeah. You need to know the rest. So you need to know the distribution. Correct? Okay. So if you know the distribution, it means that you know the full range between the smallest and the largest, and you know the frequency of those values, large and small, across your distribution. And if you have what's called a Gaussian distribution, which was described by Frederick Gauss, that's why it's called Gaussian. There's no special anything about that. It's just someone's name. Okay, Frederick Gauss. So he described the normal distribution. So a normal distribution is the one that all of you know, you should know, especially if you're data scientists, which is you have two tails, the minimum and the maximum, right? And in the middle is your mean, your median, and your mode, and they're all the same. Okay? That's a very specific distribution that's key to pretty much everything we do. So, and I'm not going to go into the difference, I'm not going to kill you guys on statistics, but I just want to introduce you to the idea that you deal with statistics all the time. So what if you do not know the distribution? Is that a problem giving me the answer of the maximum? If you don't know the distribution, you don't know the distribution. Can you still give me the maximum? So how could you give me the maximum if you do not know the distribution? There's only one way. And what's that? If you don't know the distribution, you don't know it's normally distributed, how could you find the maximum? Don't be fooled into thinking this is a complex answer. It is not. But how do you know? What do you mean higher values? Yeah, but how do you know it's the maximum? Comparison to who? Ah! That's it. That's the only way you're going to know, is if you have all the values, right? And you rank them. You sort them, and you find the maximum and the minimum. But what if you have the population of India? Are you going to have all the values? You're not, right? I mean, you could try, but I suspect you're not going to get all the values. Correct? So then how do you get it then? How do you get it? Yes, exactly. So there's statistics. If you do not have the entire sample, then you need to find a way to estimate that distribution. That is inferential statistics. That's statistics, okay? So just describing your data, that's part of statistics, but that's called descriptive statistics. But if you want to learn about your distribution and perform what is called expectation, then you move to the next level and you're performing inferential statistics. So random sampling is how you do that. You take a representative sample from your population and you measure that. And that's from that sample you're going to infer the greater population. And obviously the larger your sample, the closer you will get to your full population. And there's also another theorem called the central limit theorem, which says that if you sample repeatedly, right, then you're going to get a better estimate of your true mean of the population, okay? So that's statistics. So why do I bring this up? Because all of this noise stuff and signal to noise and everything we do relies heavily on it, okay? And when you're going to be dealing in our world of medical imaging, you can't ignore statistics. So as an engineer, you want to, because all of you didn't put your hand up, right? You desperately want to, but you shouldn't, okay? And you're not going to be tested on statistics. No one's going to test you on statistics, right? You're not in my class, right? So don't be afraid to learn a little bit more about statistics because it will help you in your job, okay? So what am I talking today? I'm talking to you today about data heterogeneity, all right? And the reason we're interested in it is because data heterogeneity impacts model performance. So your job as an engineer, you're trying to, develop the best model possible. But unfortunately, it's not an easy task. So I won't even go there. So what I would like to help you perceive is, what do I mean by that? Okay? So let's say I need to pick out somebody wearing a red shirt in this classroom. Would it be easier to pick out that red shirt if everybody in the classroom except for that one person with a red shirt is wearing a white shirt versus everybody in the classroom wearing different colored shirts except for one person who has a red shirt? So which is the easier task? Well, yeah, duh, right? I mean, you guys obviously figure that out. But that's the difference between heterogeneous data and homogeneous data. If it's homogeneous, it's much easier to pick out the signal. If it is heterogeneous, it is much more difficult for your algorithm to pick out what you're looking for. So intuitively, if you have heterogeneous data, it's going to be more work for the algorithm. And more work for the algorithm means you need more data. It needs to learn from more data. Because you have to remember, an algorithm is not guessing. It's not estimating. It's actually iteratively going through all your samples. Like literally, it's going through all of your samples, one by one, not by one. And usually they're in batches. But they're going through all of your images. And not only that, but it's going through multiple what's called epochs, or epochs, depends on wherever you're pronouncing it from, right? But that means you're going through the full data, and then you're going through it again, full data, and then you're going through it again. Typically, I don't know, 50, 80 epochs. I mean, if you're really lucky, you might get away with 30. So that's why it's so computer intensive. But just imagine, it's going through every single image, and it does not understand the difference between two images. Because in terms of pixels, they're different. And so that's why, if you have heterogeneous data, it's more work for the algorithm to understand all of those different images. Okay? So that's the purpose of trying to understand if data is heterogeneous or not. Unfortunately, what transpires when you're developing your models is you just try. You just give it a go, right? I mean, everybody does. Even my lab does, right? You just try. You just, oh, okay, well, I'm going to do it again. I'm going to try it again. I'm going to optimize. I'm going to change the hyperparameters. I'm going to try a different model. I'm going to try different data. I'm going to split it different. I'm going to do cross-validation. I'm not going to do cross-validation, right? There's so many different ways of giving it a go. And you empirically stumble across the best model. Really. That is how it works. Right? It's no dark secret I'm sharing with you guys. That's how all labs work. And if they say it differently, they're kind of lying to you. Okay? So, is that a bad thing? No. I mean, but realize it's empirical. You're trying and trying. So it would be nice to maybe get a little guidance, right? To kind of get an idea that, ooh, you know, my data is actually heterogeneous. I can measure that, and therefore I can expect challenges. And maybe I should consider this model that I've used in the past that's done extremely well with heterogeneous data in ultrasound. Okay? That's the goal. So what do we do? General definition, basically I just went over it. Statistical evidence, dissimilarity or diversity among elements, whatever you would like it to be, pixels in our case, that make up a collective data set. So this is just a visual representation of exactly what I just said, multiple colors, right? Interestingly here, if you're all seated, there's a spatial arrangement. This one doesn't give one. This looks pretty random, right? But just that's keep in mind. And then you can look at standard deviation by groups, right? So there's just an idea of getting into this world of heterogeneity, which we're going to talk about, okay? So why can data be heterogeneous? We've talked about it all week, so this is nothing new, all right? Data collection methods, the way you collect your data can introduce heterogeneity. Oops. Think of that. Because very often, when the data gets to you, the engineer, it's too late. You don't know. You may not even know how that data was collected if you don't ask. Right? If you ask your user, then you're going to know. But if you don't ask, you won't know. And so will there be heterogeneity? If you don't know, is there still heterogeneity in the data? Yes. Okay. You can stick your head in the sand like an ostrich all you want. It's not going to change the outcome. Okay. Data storage systems can also introduce heterogeneity. Be careful about that. So how your data is stored. We actually talked about it this morning. Who here thinks that data natively captured by any device is stored the same way? Do you think all systems store the data the same way? So what do you think happens and you don't even know about it? Compression. Happens all the time. All the time. And unless you specifically ask, you say, hey, don't compress my data, thank you very much. I need the raw data. They will, because the IT group is not necessarily working with you. They're working for the hospital that's storing your data, and they have a mandate. They only have so much money to store petabytes of data, so they compress it. So be aware of that. So that's where here, data storage systems, if you have some hospitals that don't compress their data or compress it only a little bit, another hospital compresses it a lot. Well, when you receive the data, it may be uncompressed, right? It was retrieved. Because you got to remember that's what happens a lot too, right? It gets archived, right? It gets compressed in an archive and then it's regenerated. So be aware of that. That's a possibility, right? So that could change your data. Nature of data, of course. So that's the big one, is the type of data you have, right? So tumors, are you looking at tumors, types of tumors, different size tumors, locations of tumors? Like you just have data, like that's key, definitely. And then data integration, so we kind of talked about that when you're merging stuff and data, like if you have different types of data and you're doing multimodal and blah, 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 just imagine in the latent space how complex that is, right? So there's data heterogeneity. Okay. So this is kind of an easy one. You can't see the color too much, but these squares here are orange. So this is just a very, very easy, demonstration that, what do you think that is? That's homogeneous, right? There's a tiny little square that's orange, but in general, it's all blue. So that's homogeneous. How about this one? That's more heterogeneous data, right? So there's different types of data. Now the only thing is, what you see here is what? A pattern. So could this data be more heterogeneous? Yes, absolutely. If you take away the pattern, it would be even more heterogeneous. Okay? So this is very homogeneous, and because of it, we have a new problem. And so this one brings up the fun thing, the fun discussion, which is variation in data in general. So I remember during the earlier part of the week we talked about it. If you had no variation in data, then we'd all be twins. We'd all be identical, correct? Everything would be the same. And I wouldn't have a job as a statistician. But you do need to be careful here. Sadly. In machine learning, if the data is too homogeneous, it can actually be a problem as well, because it doesn't learn as well. It just doesn't learn as well. It's kind of like the Goldilocks syndrome. You have to kind of have that sweet spot of homogeneous to heterogeneous data. But typically, because you're doing signal to noise ratio, there is going to be always a little bit, right? And so it should be okay. If generalizability is not an issue for you, then having very homogeneous data is probably going to be okay, right? But if in a clinical setting, that's just not common, and so you do want it to generalize, and if that's the case, then you will expect some variability. Okay. So this is heterogeneous, and in this case, and actually worse if this was all jumbled, it's harder for the algorithm to convert, okay, because of the noise, the patterns, the conflicting patterns. This one's not necessarily too conflicting, but if you had like a big mix of it, the conflicting patterns is going to make the job for the algorithm to learn more challenging, okay? So what we're trying to do is find a sweet spot in your training, okay? And that is, and everything we've talked about so far is dealing with that challenge, right? Dealing with how do we train something successfully, considering, I don't even know if it's barriers, but it would be challenges that may exist in your data, okay? And so just remember, there are so many different contributions to heterogeneity that you need to manage it, okay? Okay, so what does heterogeneity typically do? It makes it harder to learn, and therefore, if you don't have enough data or you don't train enough, then you get a drop in accuracy, okay? Especially if you have imbalances and you have bias and everything we've talked about. We don't have to go through that again, but that's going to create a big drop in accuracy, okay? So that's the reason that you're interested in dealing with heterogeneous data. And then the easy ones, of course, is if you have easy biases that you can address, then that's pretty easy, right? You balance your data sets, everything's good, correct? Like it's pretty straightforward, right? We've done that. Okay, so class imbalance, which we've talked about at length. Feature distribution mismatch, so that one's, we're getting into a little bit more tricky stuff, right? So that's features of your imaging that you're going to be looking at. And if you have the possibility of knowing the distributions, then you can play around with that a little bit and address heterogeneity that way. But for this workshop, the one easy one to remember is class imbalance. So make sure that your certain biases that may exist in your data set that could be related to your outcome are balanced, right? If they're not related to your outcome, is it a problem? If you have a class imbalance, let's say you're training for brain tumor, okay, and detection of brain tumor using segmentation, and you're looking for a pattern in the tumor within. Let's make it more complex. We're doing radiomics, remember? Because you guys did radiomics with Ernest. We're using radiomic features, detection, cancerous yes, no, within a brain tumor. Yeah? Okay. One of the variables in the data set is grossly imbalanced. But that, instead of it being, let's say, sex that could be related, right? Let's say there's certain patterns that are, more observed in males and females, and then you have an imbalance across who has, tumor yes, no, right? Then that could cause a problem, correct? But what if it's, what they prefer for breakfast? Like, clinically, I don't think their preference for breakfast is going to impact the tumor type in their brain, right? So if you have an imbalance in that data across who eats breakfast, who has cancer or who doesn't, I don't think breakfast preference is going to have a big impact, correct? And how many other variables could you think of like that could exist in your data set? Actually infinite, right? It's actually infinite because you don't even know. There are probably so many different things that you could describe about your patients, habits, history, family history, lineage, where they live, what kind of pets they have, right? So is that going to impact your research? No, it's not. So you don't have to worry about those. You only need to worry about the ones that are related to your outcome. So they have to be there has to be an imbalance, and it also has to be related to your outcome. Both have to be related to your outcome. Does that make sense? Okay. Okay, so then what we're trying to address is how can we estimate the sample size required to do the training? So you guys, are not there yet, I'm assuming, but that's probably the number one question I get asked, hands down, by any project, period. Every time I'm brought into a new project, the first thing they ask is how much data do we need? Always. It's the first thing they ask. And I always say, as much as possible. Because that's the only answer I can give. I know for a fact, the more data you give me, the better I'm going to do. Period. For a fact. But unfortunately, it's not financial data where you have too much data. I mean, there's so much financial data, it's ridiculous. It's medical imaging data, which is very costly. It's very expensive. A CT, an MRI, they're expensive. PETs, ultrasounds less so, X-rays less so, but still, they cost money. So for them to give me hundreds of thousands of data points is prohibitively expensive. So that's the reason they ask, how many do you need? We have 100, is that enough? Well, I mean, I can give you an approx number, like minimum, like 200 to 500 per class, minimum, right? But I don't know. Honestly, I don't know. And it's because I don't appreciate the heterogeneity in the data that's related to the ROI. I just don't know that. And so that's what this is. How can we possibly get a little insight into the heterogeneity? So heterogeneity in stats or math can be measured by various means, and I'm not going to trust me, I'm not going to hurt you here. But there's kind of classic ways. Shannon entropy is probably the go-to for measuring randomness. So basically, in terms of a concept, it measures the amount of uncertainty, okay? Or randomness. Uncertainty is often related to randomness, okay? In a probability distribution. So that's the stats. Everything in stats is probability distributions, okay? But the measure of randomness within a probability distribution is going to give you an estimate of uncertainty, entropy, right? Okay. There's a couple other measures. As in anything, in all presentations, we always give you, well, there's this one, and then there's that one, and there's this one, and so, Rennie's another heterogeneity measure, and it's, it's a generalization of Shannon, So you're kind of like, why are there so many of them, right? So in statistics, there are always different measures, because for all these measures, they have different assumptions, or they have different interpretation, or different meaning. So they may actually give you heterogeneity, but there's a subtle difference to it, or there's a subtle difference in the assumption. So that's how this essentially works. But for instance, this one, it emphasizes different aspects of diversity. So this one tends to be used in ecology, for instance, right? The Simpson index is, Simpson is in ecology. When you're dealing with communities and you want to calculate entropy within a community, you use Simpson, and then Gini Simpson is an adaptation to that one, which addresses some of the limitations of the Simpson. So there's another example of why you would calculate it differently. It's because it addresses limitations of the previous one. So you get it. I'm not here to teach you stats, but I just want to show you that there are different ways of measuring the same thing, and you need to pick the right one. Just like everything, right? In this case, we're going to take it one step further. We're going to create a new one. Why use what's already there, right? No, I'm kidding. It's just so that this is more applicable to what we do in imaging, okay? So this is the heterogeneity index, the HTI, and it's a variation of this Shannon entropy. So that's why I was saying we'll just stick to Shannon. But we're just basically doing exactly what Shannon does, but we're applying it to like a space for imaging. Okay, and this was first applied to transcriptomics, and if you don't know what that is, it's basically we're looking at transcription, gene transcription. As you know, DNA is the coding, right? But it's the coding for the production, typically, of protein. And you have to go through steps. You go from your DNA to your RNA, and then the RNA is transcribed. And there's different steps like that. And so it governs where does protein get expressed in the cells in your body. Because inevitably, you don't have the same proteins expressed in every cell in your entire body, or you'd just be one big blob. Right? You'd just be one big blob of cells with proteins, all the same proteins. That's how we differentiate, right? So expression is transcription. You're assuming that the proteins are made, but it's transcribing. It's just a way of looking at differences. And so I'll show you pictures later of how it works. But this is where it was first established, was in transcriptomics. Okay, so once again, the HTI looks at one area, and we have 3 traits. So 3 traits in genomics, right? In genes, you have 3 different traits, and they're being expressed in the same area. And what we're doing, you may not see in the color in the back, but this is all blue, this is all orange, this is all green, and then these ones here are all systematically alternated. Okay? So when you look at that, if you only look at HTI, which is the index, which looks at proportion of the traits within one given area, essentially, it captures heterogeneity at the global level, but it lacks the ability to account for local level. So that's the first concept that's a challenge here for you guys, and that is spatial resolution, location, right, of your traits. And so what's been developed, no surprise here, is we're just taking the HTI and then we're breaking it up into a grid. You can't see the grid lines maybe in the back there, see? Okay, we're taking it and splitting it into a grid, calculating the HTI and then taking the average, okay? So that's one way of introducing the concept of spatial heterogeneity. Make sense? Okay. So then when you look at that, you can, this is synthetic data, of course, but what you can look at is heterogeneity maps. And in doing so, you can see here the different combinations will have varying levels of heterogeneity. So these blanks here are where there's nothing, there's no trait. And that comes in transcriptomics because if you look at it, comes from pathology. When you take a slice, a sample, tissue sample, and you put it on a slide, and then you do, staining, right? And you get the different stains. You'll have areas that just don't have cells, right, on the tissue. So that's what this represents. In our world of CT and MRI, pretty much will always be something, except for on the outside of, CT or MRI. But anyway, you'll see here, this has very low heterogeneity. This has higher and high, both are about the same. Okay, they're very heterogeneous. That makes sense, because if you look within each square, the proportion of the different traits is almost equal, right? You have a little bit of all 3. But if you look at this one, there's nothing there. But this one's all blue, right? This one's all orange. This one's all green. This one's all red, right? So then within those squares, it's homogeneous. Make sense? So if we were to apply this to MRI data, which was done, in this case, what we're doing is we're taking pixel intensity, we're setting a threshold, and for different sequences, PD versus T2, we're saying, has it matched the threshold, yes or no? So that's our trait, right? And then we're combining them to then compare it for the HTA. Okay, so instead of genetic traits, we're actually using thresholds for pixels. So what does it do? It permits us to then estimate the heterogeneity within one brain, right? So there's multiple slices of, multiple sequences for the same slice, but it's one person's brain, right? So within that brain, how much heterogeneity exists. And if you look at the sensitivity analysis, so this is to show you, because I'm sure all of you were thinking, I have a problem with my method, don't I? Was I really thinking that? So the problem is, what's the number of regions? What's the number of regions? And how does the number of regions affect the calculation of my HTA? So think of it. If I only have one region, that's actually the HTI. I'm not taking the average of anything. I only have one value. It's the HTI. So is that heterogeneous, yes or no, if I only have one area? Yeah, it is heterogeneous, right? Because I have a mixture. But if I then go up to splitting it more and more and more and more, you can see that the smaller my squares become, right? What happens? What happens to the HTA? It goes down because it makes sense that if you get down to a square that's one dot, what's the color of the dot? Blue. Is that homogeneous? Yep. So then it's, right? So do you see immediately the limitation? So that's the reason it's a PhD project. If it was easy, then we'd be done. But it's not, because what we need to learn in order to make this happen is understand that relationship between the size of the grid, how we determine the traits to make the calculation, and then, we're not even done then. Let's say we do that and everything's fantastic. Then you guys are going to say, so what? Like, you give me a number, 4. Okay, it's 4. And you're going to be like, what the heck is that? What's 4? What does that mean? I don't even know what that means. So then what we need to do is associate it to learning in machine learning. So that's why it's a PhD project, because it's not easy, right? So, and then, do I really care? I mean, do I? I'm actually asking you, me personally, you know me now, I've been yapping up here all week. Would I be interested in knowing heterogeneity in one brain? Do I care? Do I care about the heterogeneity in your brain? Do I need to know that? Just one person? No, right? I need to know the heterogeneity across brains, right? Yes. So then, now we need to adapt this method to all of your brains. So now can we calculate heterogeneity across brains? So what we're going to do is these, simplistically, these grids will no longer be within a brain, they'll be across brains, right? So we're going to, each brain is going to be an area, and then we're going to compare across brains, because if everybody has the same brain, then it's homogeneous. Does that kind of make sense? The other challenge, of course, is going to be what do you use as a trait? So in this case, in the example of where it was used within a single brain, it was used for MRI in different sequences. Now that could work for MRI and brain sequences, right? But what if you wanted to use it in X-ray, or if you wanted to use it in video? Let's say you wanted to use it in video. You're taking frames from a video that you were recording a patient doing a task, for instance, behavioral research. So then how do you use it then? How do you know if those video frames are heterogeneous or not? Right? That's tricky, because you're not going to use sequences for MRI, because there's no MRI, it's video. So we're using radiomics. So taking radiomics, which is the study of the distribution of your features, right? we'll use those as thresholds, right, to kind of say, oh yeah, within that area, for that radiomic feature, this is the level, yes, no, or multiple class, right? And that will provide us with the traits, right, to then assess heterogeneity. But once again, there's another, ooh, I don't know if it's going to work, is what radiomic feature do you use? What kind of thresholds do you use? What's meaningful, what's not? So that's the reason, she's working years on this as a PhD. Make sense? But that's where we're going. I don't even know if it's going to work, really. Hopefully Rosa's not listening, but no, but I mean, joking aside, that's research, right? I mean, that's why you do research. If I knew the answer, I wouldn't need a student to work on it, right? I mean, obviously we're confident, but who knows, right? And that's it for heterogeneity. Whew, we're right on time. I love it. So I think that's it for diving deep into the engineering part. And then tomorrow I get to put you to sleep with ethics and data security and all that stuff. But sadly, it's equally important, right? Because as engineers, if you don't get any data, can you do your job? If you have no data, can you do your job? No. You'd have to make it up. And then no one's going to be interested in your work because it's made up. And so if you can't get data because of the security or the privacy issues, you may as well take up another job. It's not going to work, right? So then inevitably, learning to deal with ethics and privacy is very important, okay? And that's what we're going to talk about tomorrow. But for today, before we finish, are there any questions on data heterogeneity or the concepts of heterogeneous data? Anybody? Questions? No? We're good. Yeah, I'm not too surprised. Oh, thank you. Taking pity on me. Yes.
So now for meditations, like I said that this is, for example, so from human bodies different from each other. Like,
yeah.
The response is different. I mean, what is it that you think? I do not know anything of medical just so that model. But when you talk about heterogeneity, then in case of diagnosis, don't you think it will be a big challenge?
No, I think it will be a big.
Because to analyze, for example, I'm taking patient 1. Okay, so they are different. And this is what is the diagnosis that you know for will be different than the other one.
Yes, it will be.
How is heterogeneity able to allow you to have a proper decision making?
Oh yeah, no, absolutely. That's the challenge. Absolutely. So you've nailed it right on. And so the purpose of the work is to figure exactly that out. So we're going to start from very basic. So exactly as you said, one person's brain is different from another's. So if we were to just look at within that the entire picture of that brain versus the entire picture of this brain, then that's one thing, right? That's one. If they're identical, if you look at twins, or if you look at the same person twice, there'll be no differences between them, so that's homogeneous. Because we're looking at the entire brain here. We're not looking within the brain, remember? Okay, so because if we look within the brain, then the data can be heterogeneous within a brain. Right. So in this case, we're looking between patients. So we're looking at, the comparative value is going to estimate, let's say, the entire brain. So if it, just think of it, if you get a value for one person, it's 3. Making it up, 3. And then you take that person again, same scan, what's the value going to be? It is 3, it's the same person. But what if you took someone else, and their value is 3? And you take someone else and it's 3. And you take everybody in this room is 3. That's homogeneous data, right? But if the values are now changing across people, then that's heterogeneous data. And so that's going to be, if the values are, if it's heterogeneous across everybody, then we associate it with how much does that challenge training, right? So we'll train it with homogeneous data and then varying levels of heterogeneous data, and then we measure the score of heterogeneous, the HTA across all of those, and then we measure the time and the requirements for training, and we're going to see that, you know, when it assume, you know, homogeneous, a less heterogeneous data set is going to train with less data and quicker, and a more heterogeneous data set is going to train longer and require more data. That's literally what we're going to do. But it's not easy. Like, that makes it sound easy, isn't it? But it's not at all, because you can imagine if you're looking for a brain tumor, at that level, everybody's brain is basically the same. Yes, you know, you're right. It's a little different here and there. You have different size, and you have, you know, whatever. But we all have the same brain. Anatomically, it's the same. So that's homogeneous, correct? And that's all dependent on the traits that you choose. But if you're looking at a summary value like a radiomics, probably it's going to be very similar. So then, depending on where that tumor is in your image, that's where the heterogeneity is going to be, or what's surrounding it, or exactly as you said. Maybe the process has deformed the brain tissue in that area. So now it's different. So then that's where we need to start playing with, should we create grids within each person's brain, right, to look for heterogeneity with it, to measure that heterogeneity. So exactly like the slide I showed here, this is what we need to be aware of. This is what we need to be aware of, correct? Like, how are we comparing the areas? Because if we compare the whole brain versus sections of the brain, within the brain or between brains, that's going to be what we're working on. Make sense? But you see, right now, for all of you, you can just absolutely forget everything I said, because you're not going to do anything with it. You're just going to try it. You're just going to give it a go. And then you can say, I need more data, please, right? Because that's what's going to happen. You're not going to train successfully, and you're just going to say, I need more data. But that's what we're trying to do is provide a little insight to that process. Make sense? Any other questions? We have 10 minutes. Jeez. So no, I'm kidding. So for heterogeneity, we're done. Next would be, all right, we'll leave that on, get the light. Anything on this morning? Any questions on this morning? Like the whole process? Upscaling, blurriness, noise, that process? No, we're good? No, we've got that one down? Yeah? Yeah, it's not an easy topic, but it's one that, as I said, is what you're going to deal with the most, okay, when you get into the space, for sure. And the reason you're dealing with it is essentially the introduction of heterogeneity into your data set, or the loss of signal. So basically, any kind of blurriness, any kind of pixelation, even brightness and contrast, what happens is you potentially lose your ROI. So meaning the region of interest is no longer visible to the model. Okay, so what is required to make the decision is not visible anymore, or is obstructed, or is not clear. That's it.
The normal data set what is available, it's in 2 KPs regarding the state. I think this is where I need to concentrate on that. Resolution change. Like when you're feeding with the model,
yes,
the resolution should be less. Otherwise,
well, the resolution will be forcibly less if you have a very high resolution image. Yes, because they're designed for a specific size. So they were kind of 128 by 128 for the longest time. 256 by 256 these days, and now some models are going bigger to 512 by 512. Anything bigger than that is pretty rare, because it's computationally too expensive to load up all those images into the memory of the computer to do the processing. It's just too much. And they also showed that, for the level that we're working at, 256 by 256 and 512 by 512 is actually really good. Right? So it's all dependent on what you're working on. Like if we're going to do a 15T, MRI, well then yeah, you know, 256 by 256 might be like, what's the point? Like, you're just losing everything, all the advantages of a very high Tesla MRI, right? So that's what's going to change it. If you look at ultrasound, I mean, wow, right? It's pretty crude. Now, the other thing is they're coming out with high-resolution ultrasound that exists now, and it's actually stunning. When you look at high-resolution ultrasound, you're like, oh, what? That's an ultrasound? It's amazing. Yeah, but like, so the question would be, it's all relative, right? So, are you losing? That's the question. Are you losing? You may not be. So, what's the resolution you're working at? Like, what's the resolution you're getting the images at?
But I have the data set.
Yeah. And so, what's the resolution? Well, yeah, but that's just size, right? So you have to know, because it all depends. I mean, if it's just a black image, then it could be that, right? But it just depends on it. But you just have to see if you're going down, how far you're going down. You're going to lose information. But the thing is, if you're going down to 256 by 256, you're probably fine, right? If you're going up, no, that's where you lose, right? If you got a small, as you say, that's what you're concerned about, right? That you might have a 50 by 50 image, and you need to bring it up to 256 by 256, right? Yeah. So that's the biggest problem. That's a huge problem. That's a for real problem. That's what machine is saying. Padding and then upscaling is one way. And then I was poking her a little bit. There are now some diffusion models, some what they call super resolution CNNs. Those are models that they're trying to do exactly that. They're trying to take that 50 by 50 image and upscale it without loss of resolution. Because if you just upscale it, you lose it. Inevitably, it gets pixelated. You lose it. But you have to have a trained model to upscale. Right? I mean, you can do VAEs. People have done that as well. Encoder, decoder VAEs. But the problem is they hallucinate. Because that's not what they're designed to do, right? But diffusion models are generative, right?
She's asking reduction is bad.
Oh.
That I know.
Oh, yeah. You mean like in terms of, are you doing image analysis?
Resolution of PET because it comes in high resolutions.
Yeah, but that's
If
okay.
I want to feed that.
So just the image itself? Then you can.
Image.
Yeah, but an image is an image, right? Yeah. So you have an overlay, right? You have PET over MRI, right? And you're using the combined image after you've dealt with all the distortions and all that fun stuff, right? But you've got an image, right? Yeah. So then you're just gonna downscale it, and that's okay. That's okay because you're going from high to low, and so as long as the algorithm that's downscaling it, you won't lose crucial information because you're going from really high resolution to less resolution, but the less resolution is exactly what the algorithm wants. So yes, you will lose information, absolutely. And is there the possibility you'll lose a little bit of signal? Yes, absolutely. Absolutely. But typically you're okay. Typically you're okay. Because of the way it works for downscaling, it's okay. Right? Because it's just taking surrounding pixels. You should be all right. So I wouldn't, don't quote me on that. But I would say you're probably okay. Okay? For sure. And there's definitely a whole bunch of different ways to downscale with minimizing loss of information and stuff like that. Yeah. Okay. Any other questions? That was a good one. That was a good one for sure. Because there's another common problem, right? And as I said, I mentioned compression. So upscaling, downscaling, and compression, kind of similar, happens all the time. Compression happens all the time. That's what JPEG is, right? You guys all use JPEG. That's the compression format, right? And so they need, those compression algorithms need to make it smaller, and to do that, it loses information because it just takes surrounding pixels, right? And so, unfortunately, there's a loss of information. But usually within the window that we're working at, it's not bad. But if you really compress, it's a problem, right? A little bit of compression is okay, but a lot of compression then damages the image. Because when you come back, it's not the same anymore. You can't, right? Once you've compressed an image, it's compressed, right? So for you to uncompress it, you've already lost the information. So it's kind of a done deal. Sure.
Like which image format is better? I mean, JPEG or PNG,
Um,
sometimes I think but if you take PNG or JPEG.
So I would say it's a great question. It's kind of a flavor thing, you know, people's preferred flavor. But I would say in general, it's PNGs. In general, it's PNGs. Just because the format is a little bit more useful, is that the right way? It has a little bit more flexibility than JPEG in terms of, you know, reading it in, manipulating the file, all that kind of stuff. PNG is a little bit easier to use, right, than JPEG. But you can use JPEG.
Because sometimes what I do, like I am converting audio signal to image. So I'm getting spectrograms. So like every time I think whether I have to convert that signal into PNG or JPEG, like that confusion is there every time.
Yeah, I mean, as I said, like we tend to work in PNG. Most people I know tend to work in PNG, but you know what I mean?
Depends on the work.
Yeah, I mean, there's people that work with TIFF, right? There's TIFF that's being used because ultimately you're just sucking it into your algorithm. So however you read that image into your algorithm is going to be the format you need. And typically a lot of them, like a lot of the architectures are reading in PNGs, but as you know, you can convert everything to everything.
So which, I mean, usually we use 224 into 224 or like that.
Anything around
so
there, yeah.
anything. I mean,
Oh, yeah.
is there any particular like length and width? I mean, which is preferred?
Nope.
It's a general question.
Nope. It's all to do with the architecture you're dealing with, because when they built that architecture, they chose a specific image size to fit what they wanted to do, and they want to use an image that's large enough that it produces a good model, and small enough that it doesn't overwhelm the computer.
Yeah,
so that's the choice.
One question.
Yeah.
Like, even that is also one of the questions I wanted to ask. Like, the bigger size is better or the small size images are better?
Okay, so in terms of resolution and in terms of information in the image, the bigger the better. Absolutely 100%. The way you can kind of gauge if you're wanting to work in a large image size or not is going to be your batch size. So if you have very large images and you have an architecture that allows large images, because not all architectures do, but if you do, or if you modify the input layers, right, so that you can take on a big image, then what's going to determine whether you made the right choice is your batch size. So for instance, your computer may just be overwhelmed and you're going to have to work at a batch size of 1. No, right? Like it's not going to work. So then that you're going to have to once again find that sweet spot of batch size, like how many images per batch works best for learning and doesn't overwhelm your computer system. And so that's what's going to determine it ultimately. That if it's too big because you just don't have the computer to do it, then you're going to downsize. And then you downsize to, you know, like an image size that's still going to be efficient, right, for what you want to do, your task. But that's essentially what determines that combination. Yeah. Not an easy question, because everybody suffers that problem, like literally everybody. When you do any work, the first thing you deal with is that, right? Or DICOM. So you guys may not work in DICOM, but DICOM's a pain in the you-know-what. Like it's just a very heavy architecture, like a format, sorry. But everything in medical imaging comes in DICOM. So typically you convert it. So either, as Ernest said, most often you're going to convert it to Nifty if you're working with three-dimensional space. And if you're working in 2D space, then you're just going to move it right to PNG or something like that. But you're going to convert it out of DICOM. There are DICOM libraries that you can read in directly DICOMs. You know, the only reason you would do that is to lighten up your pipeline, right? Because for training, it doesn't matter. You can, you know, the architecture doesn't care, right? The image, pixels are pixels, right? Or voxels are voxels. But it's afterwards when you're going to, you know, put the algorithm into use in your hospital. you have to think of your input. So if your input is a DICOM file and you train everything on Nifties or PNGs, well, that's not going to work. So then that means that in your pipeline, you're going to have to convert your DICOM that you're receiving, convert it, and then put it into your algorithm for inference. And it will work, but the thing is, it will slow things down. So then if you have a very prominent radiologist sitting at his or her desk and waiting for the answer, you don't want to make them wait for too long, because if you do, they say, your software is crap, and then you don't get it, right? So that's the reason. So literally, it would just be for latency. All right, okay, thank you guys. Look at that, right on time. I think we're doing lunch, and then when we come back, I get to listen. At 2 o'clock, sorry, when you come back at 2 o'clock, I get to be the audience.